we're going to see in this section that Ka and Kb are related to each other for a conjugate base pair. We will see that if we consider our favorite substance, ammonia, are always our favorite, right? Plus water, if we just do our standard Kb, we get our OH minus and NH4 plus. That's Kb. This is an equation for Kb. If we want to do an equation for Ka, a Ka equation looks like the following. This is a Ka equation. And we will see that there's a special relationship when we multiply Kb times Ka. Remember, if we add equations together, we have to multiply the K's, right? That's how Hess's law kind of works for equilibrium constants. So if we add these two equations together, NH3 plus H2O plus NH4 plus, we have OH minus plus H plus NH4 plus NH3. And as we know, if something is on both sides of the equation, cancel it out. What the heck? H2O turns into OH minus plus H plus. Go figure. And if we consider the Ka or the Kc for this equation now, OH minus plus times H plus, which as we know is Kw, or 1 times 10 to the negative 14. So Ka times Kb for a conjugate acid-base pair is always equal to 10 to the negative 14. So once we're given the Ka and Kb, or we have one of them, rather we only need one, we can solve for the other, right? They're related to each other. So Ka for a particular acid, you can figure out the Kb for the conjugate base. This should be noted, I'm going to make it very, very clear here, that this relationship is for conjugate base pairs. For conjugate pairs. So for ammonia and ammonia, for acetic acid and acetate, for carbonic acid and bicarbonate, we can use this relationship. Again, it's only for conjugate pairs. It doesn't hold for anything else, only conjugate pairs. Does not work for carbonic acid and carbonate because that's 2 hydrogens away. Can't do that. Remember, conjugate base pairs or conjugate pairs are 1 H plus, different from each other. So with that in mind now, we can say, okay, well, if Ka, or rather Kb for ammonia, was 1.8 times 10 to the negative 5, then Ka would be 1.0 times 10 to the negative 14 over 1.8 times 10 to the negative 5, which will equal, let's see, 1 EE negative 14 divided by 1.8 times 10 to the negative 5. Always watch your parentheses here, or use the EE function on your calculator to avoid any sort of accidents for parentheses. We get 5.55 times 10 to the negative 10. So what does this mean? What does this mean for us? So Ka for ammonium is 5.5, I guess we need to have the same sequence, 5.56 times 10 to the negative 10. Kb for ammonia is 1.8 times 10 to the negative 5. What does this information mean to us? If we look at the numbers, we see one of them is bigger than the other, right? This is a way we can compare things. we can see from these numbers that ammonia is a much better base than ammonium is an acid. We will see if Kb is greater than Ka, the base is more likely, is stronger. The base form is stronger than the acid form. If it's the other way around, the acid is stronger. And so we'll be able to say, okay, well, we've got, these values. We can see which one is kind of more preferred. Are we more likely to see ammonia as a base or ammonium as an acid? Well, the base is stronger there, so it definitely prefers that. Generally speaking, if the Ka is bigger than 10 to the minus 7, we can say also that the acid form is stronger. Because Kb must be then less than 10 to the negative 7. Because remember, Ka times Kb must be 10 to the negative 14. So if Ka is bigger than 10 to the negative 7, Kb must be less than 10 to the negative 7. And so we can say again the same thing here. If Kb is greater than 10 to the negative 7, then the base is stronger of the pair. So it's not necessarily comparing bases to each other. You would just use the Kb values of the two bases, but it's merely just like evaluating what the preferred form is. Is this thing more likely to be an acid or a base in solution? And we see that for these relationships, we can identify those. One more thing you might see, by the way, is pKa and pKb. We use this p idea, which is the negative log, to talk about very small numbers. So you might see pKa instead. And the pKa is simply the negative log of the Ka. And pKb, of course, would be the same for B. You might see these numbers presented because they're easier to work with. For example, for ammonia, the pKb is 4.74. And that's an easier number to work with than 1.8 times 10 to the negative 5, right? It avoids the exponents idea. And if we remember, pH and pOH would add up and equal to 14. It's the same thing for these two. pKa plus pKb will also equal 14 at 25 degrees Celsius. And so we can figure out for ammonium, the pKa therefore would be 9.26. I'm just doing that math in my head, but we can do that here. Therefore, for ammonium, the pKa is 14 minus 4.74, which is 9.26. So we're able to calculate it that way. And just like before, the Ka would be 10 to the negative pKa, or Kb would be 10 to the negative pKb. So you can go back and forth. Just like we did with H plus concentration, we can do all the same things with Kas and Kbs. Let's kind of conclude this section by talking about just evaluating and comparing Kas and Kbs. So a stronger acid will have a higher Ka than another, meaning if we're comparing two acids. So let's just say this. For acids 1 and 2, those two acids, a pair of acids we're comparing, if acid 1 has a higher Ka, has the higher Ka than another acid, then acid 1 is stronger. And if acid 1 has a higher pKa than acid 2, then acid 2 is stronger. pKa and Ka are the opposites. So for an acid to be stronger, we're looking at either a higher Ka or a smaller pKa. Just like for acids, right? Low pH means highly acidic, which means a high concentration of H+. When we're comparing the equilibrium constants, a stronger acid has a higher Ka or a lower pKa. And you'll see that trend if you look on Discord in our chart of Kas and pKas, that it's organized such that the Kas decrease over the chart. So we start at the highest Ka and we go down. We're going to start at also the lowest pKa and go up as we go down the table. The pKas increase as Kas get lower. So there's that opposite relationship. All right. So with that, that's it for this video. In our next video, we'll evaluate salts, things that we may not consider to be acidic or basic, but will in fact have an effect on